Okay, 6.5. We're now looking at the graphing aspect of trigonometry. We're looking at trig functions. Trigonometry shows up in a lot of aspects of real life. We've got things like the number of hours of daylight in this question here. We'll have the tides, how the tide goes up and down. When a pendulum swings, or if you're at an amusement park, the boat that swings back and forth, those kind of things. And all of these different applications are periodic applications. They repeat over and over again. So when we look at this one here, we're just going to read the graph. Approximately how many hours of daylight are there in the longest day of the year? We're looking here for the maximum value, which is up here. And we say, I don't know, it looks like it might be about, let's say, 21 hours. And then approximately in the shortest day is going to be your minimum amount of light, which looks like, hey, I don't know, maybe about 4 hours. Why is it reasonable to expect the pattern to repeat annually? Because the year goes over and over again. The Earth goes around the sun. It's a periodic application. So this next page here is just really saying that we can make equations. We're making x the independent variable. That's the angle. So x is your angle. And most often we're going to talk in radians. Could be done in degrees as well. But x is the angle. The y value is your ratio. So in each one of these, it could be the sine ratio, the cosine ratio, or the tan ratio, depending on which one we're graphing. And as you discovered in 6.4 in the math lab there, is that sine and cosine are periodic functions. That are continuous. They continue up and down. And that's what it's saying here, that a periodic function is one that repeats at regular intervals. And the length of each interval, how often it takes to repeat, is called a cycle, or a period. Let's look at sine of x. It repeats every 2 pi because it takes one whole time to go around the unit circle before you're back at the same place. To get back to there is 1 time around the circle, or 2 pi. And then when we have a graph now, we've got straight through the middle here a center line, or I call it the midline. It's not necessarily the x-axis. It is in this circumstance. But once we start doing transformations on it, that midline is not going to be at the axis. From that from that midline to the maximum value is called an amplitude. It's also the same as from that midline to the minimum. It's also the amplitude. The period is the distance from any part that repeats. So from a minimum to a minimum, that's a period. From the maximum to the maximum is also the period. From an x-intercept on the way down to an x-intercept on the way down. We read left to right, so I'm saying on the way down to on the way down. That is also the same distance. I could have went from on the way up to on the way up is also a period. Anything to where that spot repeats exactly is called the period. Our domain then. Hey, we can have any x value for our sine. We can find the sine ratio of any angle. That's what it's saying. The zeros. How often are the zeros? Well, the zeros happen, you can see them at 0, at pi, and at 2 pi, or going in the negative as well. So we've got our form, our general form again, that it's any multiple of pi. I like to use the letter n. So any multiple of pi where n is an element of the integers. And the function has a maximum value. The maximum value is going to be 1. You can see that right here. The minimum value is going to be at -1. So our range is between 1 and -1. So talking a little bit about the range, because that's where they really focus on when they're looking at a graph. They very often ask you for the range value. The reason that it's 1 and -1 is because the sine ratio is equal to, in our unit circle, we would say the y over the r. It's equal to your opposite over your hypotenuse. And we're saying from a triangle, what has to be the longest side? Well, the hypotenuse has to be the longest side. So there's no way that I can take some opposite side of a triangle and have it longer than the hypotenuse. So this sine value can never be larger than 1. And then when we go into standard position, we could have positives or negatives. The opposite always has to be smaller than the hypotenuse, so it cannot be less than -1, unless we start doing transformations. But that's why we are between 1 and -1. Likewise, cosine also has a domain. I can find the cosine of any angle. The zeros now, though, are going to be different. They happen at different spots. And as we see, it happens at pi over 2 and 3 pi over 2, positive and negative. So it's got the form of, and this just starts getting really confusing. I'm going to change it up and say the first positive answer, just like the general solution I was talking about, the first positive answer is pi over 2, first time it happens. Plus, how often is it going to be to the next ones? And it happens every multiple of pi. Let's go to our unit circle and see why that's true. We're talking about cosine. On the unit circle, the cosine is your x value. Remember, it's cos, comma, sine. So where is the cosine 0? That means where is the x value 0? That's all we actually care about. And the x value is going to be 0 here. Oh, shit, that's at pi over 2. Where else is cosine 0? That's going to be, right here at 3 pi over 2. And then again there, and then again there, and around and around and around, either direction. So the first positive one is pi over 2, and then every multiple of pi from then on. Same thing could have been done when we talked about sine, just on the other page there. The sine value is the y-coordinate, and we're looking where is the y-coordinate equal to 0, and that's going to happen at 0, and then pi, and then 2 pi. So the sine's zeros, this one's for sine, this one was for cos. Sine had its zeros at 0 plus any multiple of pi. Oh, we don't have to say 0 plus, and that's why the other one was just n pi. And for the exact same reasons as I talked about with sine, cosine is going to have a maximum value of 1 and a minimum value of -1, because the hypotenuse always has to be larger than the adjacent side. So cosine is adjacent over hypotenuse and that hypotenuse has to be the larger one, so it cannot be greater than or less than 1 or negative 1. And now you can see sine and cosine side by side there, one above the other. Anytime we talk about sine or cosine, we call them a sinusoidal function. The reason being is that they both look like sine. Cosine is really exactly the same as sine is. They're exactly the same functions, just been translated over from each other. That's all they are. They have the same center line, the midpoint, the midline. They have the same amplitude, which as we can see, the amplitude is 1. They have the same period, which as we can see is 2 pi. So some things to kind of be looking at, our center line, our midline, is halfway in between the maximum and the minimum values. So midline is halfway in between the max and min values. Or in other words, the average of the max and the min. So we're going to go max plus the min divided by 2. That gives us the average value. Our amplitude is half of the distance between the max and min. The distance between max and min is max minus min. I want to go half of that. These two formulas look almost identical. Just add or subtract and you get the other one. Now, a really important question here, because this actually gets asked on your diploma. If you're given the center line, the midline, and you're given the amplitude, how can you find the max and the min values? Okay? And in essence, find its range. And from 6.4, you saw the 3 different trig ratios, and you graph those. We're also going to be looking at transformations. Hey, that creeps into every chapter in this course. And you've got your horizontal stretches, you've got your vertical stretches, you've got your reflections, and your translations. Okay, so just being able to read a graph there, you've got one question quickly on the bit.ly there. We've got, what's the amplitude of this graph that you're seeing right there? See if you can read that graph. All right, we had a bit of information going there. I think it's time for some real graphing now. So let's graph these beautiful dance moves. First one, we got the sine of x. Looks like this. All right, nice. We've got then the next one, which is cosine of x. And then we've got tan of x. And we've got cotan x. Hey, we've got the absolute value of x looking like that. I know you're dancing there. I should have put some music on for this part. Then we've got just y equals x. Hey, x squared. We've got a circle, x squared plus y squared. Then we've got square root of x. Then we got the square root of negative x. Then we got 1 over x. Great dance moves. And then we got, oh, yeah. So now let's look at the amplitude of each one of these graphs. So first of all, let's just remind ourselves of sine of x. Sine of x starts at 0 and 0. And looks like that. So sine of x goes up through the origin. The reason for that is, back to the unit circle, at an angle of 0, and that's what our x value is. Our x value is the angles. At an angle of 0, so we're talking about this point on the unit circle, the y-coordinate, sine, is 0. So the point that we're going to be graphing is an angle of 0 and a ratio, or a height, or a y value of 0. So we're going through the origin 0 and 0. The amplitude was 1. Now when we put 2/3 in the front, hey, that's a vertical stretch by a factor of 2/3, which means multiply all the y values by 2/3. This y value, which was 1, is multiplied by 2/3, which will be 2/3. Oh, interesting. That stretch value in front is going to be the amplitude. So our amplitude is equal to 2/3. Y equals negative 4 cos of x. Well, let's look at cos of x again. Cos of x, let's go back to our unit circle. Where does it start? And at 0, cos is the y-coordinate, so the x-coordinate. So it starts at an angle of 0. It's going up to 1. It starts there at 1. And then from there, we graph. So that's what cosine regularly looks like, and then extends on the other way. So our amplitude, again, is 1 from the midline. If we take it, look at what's happening here. Negative, hey, that means we've got a reflection about x-axis. And we've also got a vertical stretch by a factor of 4. Well, if we do the reflection, that's going to flip everything over. So then we're going to be down here at negative 1. Whoops, missed that. Let me redo that. Got to make sure I get through the same x-intercept on both of those. And then we're multiplying it by 4. So now that amplitude is still 1 even after reflection. And now we multiply all the y values, which in this case is 1, or negative 1, times 4. Actually, I'll just keep it as 1, because the amplitude is 1, not negative 1. The amplitude's 1, because the amplitude's 1 here as well. It's the distance. So our amplitude is now 4. An amplitude, just like a stretch factor, can never be negative. So our amplitude is equal to 4. And of course, you could verify all this by just punching it into your calculator and checking out where is the max or the min point, how far away. And in this case, the max point, if there's 1/2, the max point's going to be the same there. The only way that that's going to change is if we do a translation up or down. That's 6.6. Now, tangent is different than the other two. The other two, sine and cosine, were called sinusoidal functions. This tangent function completely looks different. It's got lovely asymptotes. The reason for that is tan is, from the unit circle, it's talking about the slope of the line. So if we start here at 0, the slope of that line, the horizontal line, is 0. Puts us there. And as we go along, I could start drawing my lines and looking for the slope of it. If I'm over here on the other side of the x-axis, the slope is also going to be 0 again. That's at pi. Oh, look at that. Now what happens at the y-axis up here? The slope of this line is undefined. And that's at pi over 2. So the slope at pi over 2 is going to have an asymptote. It's also going to have another asymptote at the other part of the y-axis. That's also an undefined slope, 3 pi over 2. Right there. Now the tangent function doesn't have the domain like the other two, where it's any value. You cannot find the tangent of every single angle. The reason, again, is tan is y over x. Any place that the x is 0, you're dividing by 0. No graph there, asymptote. So the domain at this point is going to be anything except where the asymptotes are. So finding the asymptotes is the same as finding the domain. We're saying that x cannot equal, well, follow the same thing. Find the first asymptote, which is pi over 2, and how often is that going to happen? Pi over 2 and every pi, so any multiple of pi, NEI. The zeros, following that same process. The first one's at 0, right here, plus any multiple of pi. So n pi NEI. I don't need to say 0 plus, so I'm just going to get rid of that and say n pi NEI. And my max and min, there is no max and min, so my range is just YER. So now when we look at the period of each function, first thing we want to always remember is how often does cosine, sine, and tan repeat? So regular period of cosine is going to be every once around the unit circle. So that's going to be every 2 pi. That is going to happen. The period on sine is also going to be repeating once around the unit circle every 2 pi. Tan, however, that one was different. That one repeats every pi. Well, this 6x sitting there, that's really, from your transformations, it's x being replaced with 6x 100% of the time. Doesn't matter which chapter we're talking about. If you replace x with 6x, that's a horizontal stretch by a factor of 1/6. So what that's telling you to do is multiply all x values by 1/6. So if the cosine period, it repeats every 2 pi, we're going to be multiplying that by 1/6 now. So originally the period was originally 2 pi, but we're multiplying it by 1/6. Or in essence, we're going 2 pi divided by 6. Take that to lowest terms, and you got pi over 3. That's the new period. How about for y equals tan at 2/3 x? Again, that's a horizontal stretch. So it means we're taking the original period, which is pi, and we're multiplying it by the reciprocal of our stretch factor. So let's multiply it by 3 over 2, or in other words, 3 pi over 2. There's our new period. And final one. Boy, they're trying to be tricky on this. This is really the same thing as saying 1/7 x. So our period then is equal to This is sine, so the period is 2 pi. And we are taking the reciprocal of the 1/7, 7 over 1. So we've got 14 pi. The bottom of page 517 there gives you this. The period of sine and cosine should be 2 pi. But whatever b value we have in there, whatever stretch factor we're doing, is really going 2 pi, the original, multiplied by 1 over the b value. So 2 pi over b. Or, hey, if you're in degree mode, 360 over b as well. Tan, that one happens twice as often. Original is pi. And the same thing. You take your b value. So we've got pi times 1 over b. So pi over b. Or 180 degrees over b in degrees. And now we do some translations. We've got here an x being replaced with x minus pi over 3. Oops, x minus 3 pi over 3. And that's adding or subtracting there. Again, back to transformations. 100% of the time, that's saying a horizontal, because it's x, translation, because we're adding or subtracting, and pi over 3 units, and that's going to the right every time. And you can see that right there. We've moved the graph over to the right. In trigonometry, instead of using the word translation, we're going to introduce a new word, or two words, phase shift. So any horizontal translation is going to be called a phase shift in trigonometry. All right, so let's find the phase shift of this one. Really, we're saying, what's the horizontal translation? And the form that we're going to be looking at is x minus c, same as we've done with any of the other transformations. And we look at it and say, okay, x was replaced with x minus pi over 6. So that's telling us we're going pi over 6 units, or radians, sorry, we know the units, or just pi over 6. You don't have to write radians. Pi over 6 radians to the right. And just in case they do ask a slightly different question, what is the parameter c? The value of c is pi over 6. It's actually positive pi over 6 because the negative is already in that equation. So the c equals positive pi over 6. And let's sketch the graphs of cos of x. Let's start with that. And that was what was done there in 6.4. So all the points that we're going to graph for cos of x, really we can get from the unit circle. Let's start, we're going from 0 to 2 pi, so we're going once around the unit circle. Let's start at 0. That point is 1, 0. So at an angle of 0 radians, and we're looking at the x value is 1. So at 0, let's make the x value, let's call this 1 here, plot it there. Then we've got pi over 3, pi over 4, pi over 6, pi over 4, pi over 3, pi over 2. At pi over 2, we've got 0, 1. Which is down here. Then we go through the rest of the unit circle. You could plot those points, take the decimal form. Then we've got at pi, we've got negative 1 and 0. So go find pi and negative 1 down here and 0. And then again, you could plot those three if you want. I'm just going to go down to 3 pi over 2. And this is 0, negative 1. We're looking at just the x value. Back up. And then we're back at 2 pi to 1. And we connect those. And there's our cos of x. And because I grabbed the wrong grid paper that I should have taken a different one, I needed to go through just now and I put extra tick marks in here so that those tick marks are actually pi over 6. What I did is I took pi and broke it into 6 tick marks. 1, 2, 3, 4, 5, 6. So that's pi over 6 for the scale. So take it now and we're going to move every point pi over 6 to the right. So this point's going to move pi over 6 to the right. This point's going to move pi over 6 to the right. This point, pi over 6 to the right, pi over 6 to the right, and pi over 6 to the right. The problem is that it said that we were only going up to 2 pi. So really, this part, I don't get to graph. And then I got to add in the extra part that's going to start coming back down over here. And last one. We're going from 0 to 2 pi. We're looking at y equals 3 sine of x. So that right in front there, hey, that's a vertical stretch by a factor of 3, which really, we've already seen, means is an amplitude of 3. Well, let's start, sorry, forgot to start with sine of x. I'm going to graph it in red. Sine of x, I'll graph in red. From the unit circle again, at 0, an angle of 0, the y-coordinate of the unit circle is 0. So we're at 0 and 0. Then at pi over 2, we're going up to 1. So I've got actually this broken into pi over 12s. But we're going up to 1 at pi over 2. At pi, we're back at 0. At 3 pi over 2, we're going to negative 1. And at 2 pi, we're back up to there. So this one is a little bit more stretched out than what some of your graphs might look like, but it's still from 0 to 2 pi. The tick marks are just larger. Now we're going to take A. I'm going to do it in blue. So it's a amplitude now of 3, and that's all that's changed, is every y value is multiplied by 3. So we're still there at 0 and 0. Then at pi over 2, it's going up to 3. At pi, it's back to 0 and 0, or it's back to 0. And then at 3 pi over 2, it's going to be at 3. So we multiplied all of the y values by 3, giving us an amplitude now of 3 units. Sine of 3x, I'll do in green. This is telling us we've got a horizontal stretch by a factor of 1/3. Or in other words, the period is related to that b value. The b is 3. And sine regularly has a period of 2 pi over b. So it's 2 pi over 3. So it's going to repeat every 2 pi over 3. So again, this is telling me multiply all the x values by 1/3. From the red graph, I'm going to go, instead of it being at pi over 2 and 1, that's going to whip all the way to 1/3 of pi over 2 or pi over 6. Then this pi is going to be 1/3 of that at pi over 3. This 3 pi over 2 is going to be at pi over 2. And then where that 2 pi is now going to be 2 pi over 3. So there's one cycle, one period, but I've still got to go all the way into 2 pi. So that means I'm actually going to have 3 cycles within there. And notice that the period is 2 pi over 3. I continue that pattern. I'm going to be back up to the maximum, back down to 0, then to the minimum, and back to the midline. There's my second cycle. But there's 3 cycles within the 2 pi now. Back up, middle, back down, middle. Third cycle on the same pattern. And finally, the last one in purple. I'm going sine of x plus 3. That's on the end. That's a vertical translation. 3 up. Well, we're not going to call it a translation. Just like we don't call the translation for horizontal translation, we call it a phase shift. A vertical translation is going to be called a vertical displacement of 3 units up. Hey, we're just going to take that original red graph and move all the points 3 units up. So we're here, we're going up 3, 1, 2, 3, right there. Taking this point, and 1, 2, 3, we're there now. Taking this point, and 1, 2, 3. Taking this point, 1, 2, 3. And this point, 1, 2, 3. Connect our dots. Boom. We got them all graphed. And we'll combine all those together in your 6.6. And now you've got your final 4 points. Your A, your B, your C, your D. So you've got your A, which is a vertical stretch, or deals with amplitude. You've got your B, which is your horizontal stretch, which actually is not the period, but it allows you to calculate the period. So we can say B is 2 pi over period, or period equals 2 pi over B for sine or cosine. Then we've got our C value, which is a horizontal translation, or in these cases, we don't call them translations anymore. We call it a horizontal phase shift. And finally, we've got our D on the end. And that's a vertical translation. But again, we don't call it translation. We call it a vertical displacement. All right, and you got your final 2 questions there. The second one is really what I was talking about. That's how I graphed those. I looked at my unit circle, and I graphed them based on the unit circle values. All right. Good luck.